Hello, my name is Steve Samuel from Design Visionaries, and today's topic is hanging on by a thread. What I'm going to cover today is putting threads on things, and there's a bunch of techniques that are really important to know if you're going to be creating a tire or threads that go around a track. So, for example, here I've got a little sketch, and I'm going to put a dimension in here, a diameter, and let's say the diameter is 10, but more importantly it is P5. So I'm going to extrude that sketch. I'm going to do it as a sheet body, and I'm going to put a datum plane tangent to the sheet body. Great. So now I'm going to make a little expression, Control E, and that expression is called length. And length is going to equal P5 times PI left paren, right paren. That's pi. So what I've just done is created an expression that has the circumferential length of the surface that I've got. So now that I've done that, I can create a sketch that's on that datum plane, and I could make something that's like a thread. So let's say it's going to be a series of shapes that looks like this. That, like that. Okay, so that's what I want to emulate my thread. And finish. And oh, wait a second. Before I finish, what I need to do is take this shape and I need to copy it as many times as I want on my thread. So what I'm going to do now is I'm going to go back to the expressions editor, and I'm going to create a variable called n. That's going to be a unitless number that has an arbitrary amount, 20. N is 20. Pi. Okay. So now what I'm going to do is go back to that sketch, and I'm going to create a pattern. I'm going to take this geometry and I'm going to pattern it linearly. I'm going to use that as my direction, that little vector, and my count is going to be n. Okay, so there's n of these, and the pitch distance, this is where it gets really interesting, is going to be length divided by n. I think it might be divided by n minus 1 actually, because it goes all the way around in a circle, n minus 1. So there we go, and we say okay. All right, so now that I have that thread, I can then wrap it onto the surface, and it should be perfect, right? So I'm going to say curve, more, wrap, unwrap curve. I'm going to select the curves by doing infer curve, so it selects all of it like that. I'm going to select the face, and then I'm going to select the plane on which everything has been created. And as you can see, if I take that sketch away, sketch. If I hide the datum plane, you can see now that I have this thread form that's evenly spaced on the circumference. So cool. And of course, the beauty of what I've just done is I can always change this number, 16, say, and that changes the value of length. It changes the spacing in between, right? And I can change n. If I say Control E, I go to n. Where's my n? Yeah, there it is, n. And I can say, oh, I want it to be 45, let's see. All right, so that is pretty cool. Now, the reason why we go through this kind of trouble, because I could have just wrapped one of these and then patterned it with a circular pattern. The reason why is because when you get to more complex shapes, more complex than just a circle, these are the techniques that you need. So here we go. Now I have something that's much more complex. It's a tread that has been imposed on a shape that is made of arcs and lines. Okay, so there's some techniques now that are very similar to what I've used, but in order to apply them, got to do some tricks. So to do this particular model, I started out with a sketch like this. And, you know, it's just got a line, an arc, a line, an arc, a line, and an arc. But I also have this line right here because what I've learned is in order to get this thing to happen, you've got to create a datum plane that starts at a specific location that is in the middle of this arc. I'll tell you why in just a second. But going through the motions, what I've done here is instead of creating a variable called length that is just pi times a diameter, I created a length variable that is just the overall chord length of all of these entities. So in order to do that, I just went into analysis, measure, I put this on object set, I put this on curve edge, I made sure that it was associative, I went into tangent curves and I selected it, and it gave me a measurement dimension, and that measurement dimension is length. See that? So this 71 inches is the full perimeter, if you will, of these entities. Okay, then I made an extrude of just these few entities, and I started here. And for this, I had to use the stop and intersection command on the sketch. So I just did a part that looked like that. Okay. Then I did another part that looked like that. And it was very important for me to split these up. You'll see why in just a moment. The next thing I did was put a datum plane that was tangent to this little face right here, but started right at this entity, because if you want to wrap something onto a quote-unquote developable shape, you've got to start it in a place that is tangent. Or at least that's the easiest way that I found to do it. Then I did a composite curve. The composite curve was this arc entity, this line entity, and this arc entity, and that's it. So really what I've done is made a composite curve of the chord length of what makes all of these, or I should say the chord length of the entities that created this purple shape. Okay? Now the reason why I did that, why I made the composite curve, is so that I could get another measurement dimension. And I've got a measurement dimension for the overall length of this, but I also needed the measurement dimension that would start here and measure out all of these entities. And the reason why I did that is because the next thing I did was define a law curve. Now the law curve was interesting. The law curve is on this plane here, and the law curve starts all the way back here. And what back here is that offset distance from this dimension all the way out here that ensures that when I wrap this curve onto these purple faces, it wraps all the way to this exact point. So if you look at the law curve formula that I have, the law curve formula is x as a function of t starts by length times t, so that's the overall length of the whole perimeter, but I'm subtracting that offset that I just told you about, and I'm also then using a y, function of y that's a sinusoid. There's my variable a, and I'm multiplying that by sine of 20 times t times 360, so there's 20 lobes in this equation that I've got, or in this curve that I make. And so here's the curve, but I also neglected to show you or tell you that that curve is mapped onto this sketch here, where I'm using this line for the x and this line for the y. So when you do a law curve, and you go into the law curve function, which is incredibly powerful, and you set up your x of t, y sub t, z sub t, you can also go here and specify a thesis. And the way I specified the thesis was with x-axis, y-axis, making this the x-axis and that the y-axis. And that is why the law curve that I've defined is defined here. And like I said, it also starts back here. That's what's subtracting the offset from the x array meant. Great. So now that I've done that, I was able to actually wrap it. Okay? So there's the first wrap. I did this first wrap because what I've found is you can't wrap to something that is closed. You have to wrap to an open shape when you have a developable shape like this. You can wrap onto a cylinder, but when you have different sections, an arc, a line, an arc, a line, you can't just wrap the whole thing. You've got to do it in sections. So this was one section. And of course, the length from this starting point all the way to the end is the exact length that it has from the intersection of these entities, this little arc segment, and then this line, and then this other arc, and then this line. That's the length of this part of the sinusoid. And then I wrapped it the other way and put it on the purple surfaces. So just hide that now. Oops. That. Okay. Let's go back to the law and hide it. Law defines spline. Great. So now the geometry that I had was going to be the perfect drive curve for my section. And the way I made the section was to put a sketch on this path, on the end of this path. There's this rectangular sketch. Great. And then I did a sweep. So that sweep was a sweep swept. And in order to make it work, I only swept this little bit, that little section, and I made sure that I had preserve shape on so I would get sharp corners, and I swept it relative to face normals, just like that, face normals. So that worked out perfectly, and then I did a bunch more of those. And here we go. So I did a sweep here, another sweep, another sweep, another sweep, and then the last sweep, I swept from this face to that face. I had to select those face edges to make sure that it came perfectly. It became perfect. And then I united it all together, just like that. So now it's all one piece, and I can say Control W and hide the sheet bodies. And what else? Let's hide the sketches and the curves and the datum planes and all that jazz. Let's see. Stay datum plane. Oh, there you go. Okay, there you have it. And then I simply patterned it. Cool. So that's the whole litany of things that you need to make, let's say, a tread on a tank, like a tank tread, or if you want to tread on a tire. There's a lot of techniques there. Yeah, as you can see, they're all here in the model tree, so you can slow this video down and watch it a few times to get it all. But that's the kind of thing that you have to do some of these interesting shapes. You really have to combine a bunch of techniques, which in my view is a lot of fun. Again, my name is Steve Samuel from Design Visionaries. Thanks for watching. Please share this video with many others, and let's get the word out that we have this incredibly powerful software that we can use to emulate all sorts of things very, very exactly. Thanks again.